Today we will discuss about support vector machine. Support vector machines are mainly used for performing classification. Classification is the process of finding the optimal hyperplane in the space, which is dividing the two classes. So you can see in this figure there are so many hyperplanes separating the two classes. Here this is one class, this is one class, black class and blue class. But some hyperplanes, if you choose some hyperplanes, say for example these two hyperplanes, the chances for getting error is more. Okay, you can see if you select here also, again there may be some chances of error. So from this figure, if you see, if the hyperplane is situated exactly in between these two class labels, then we can say that hyperplane is optimal. Or you can say the hyperplane is optimal if it is situated far away from both these two class samples, then it is optimal hyperplane. Once again, if a hyperplane is situated far away from both these class samples, then you can call that hyperplane as a optimal hyperplane. So classification is a process of constructing the decision boundary surface. Here the decision boundary surface is a simple hyperplane. So if a point is present above the red line, means you can classify it as a blue. If any sample point is present below the red label, means you can easily tell it as it is belonging to black class point. Okay, black class. So that is how you need to understand regarding classification. Classification means you need to construct a optimal hyperplane separating the two classes. Here there are only two classes are there. Okay, this is simple class. Let us see what are the equations. How do you represent the hyperplanes in the space? So hyperplane, you can see this is the equation of the straight line. Similarly, if you are having, you can see it is a two-dimensional hyperplane. So the decision surface is W2x2 plus W1x1 plus W0 is equal to 0. If it is a two-dimensional space, the hyperplane becomes a straight line. You can see the similarity between first equation and third equation. Both are same. If you are rearranging the second equation, it will be like this. It is exactly in the form of y is equal to mx plus c. So both these two are same. Say for example, if you are having more than two dimensions, say for example 3 dimensions, means your equation of hyperplane will be w3x3 plus w2x2 plus w1x1 plus w0 is equal to 0. If the hyperplane is a d-dimensional space, means you can write wt xd plus so on plus w1x1 plus w0 is equal to 0, and you can write compactly in the form of sigma over wi xi, where I running from 1 to d plus w0 is equal to 0. This is the equation of the hyperplane. Okay, so your hyperplane is in d-dimensional space. So or you can represent in vector form also, where capital W is W1 W2 up to WD transpose. Similarly, X is also X1 X2 XD transpose. So now the point is we will understand how to calculate distance between a point and a hyperplane. How to calculate the distance between a point to the hyperplane. Say for example, you can see this. Why we are studying this formula means this formula will be useful for our optimal hyperplane calculation in SVM. So SVM is all about calculating the optimal hyperplane. So optimal hyperplane means you need to be separated from both these two classes. Okay, that is the point here. That's why we need to understand how to calculate the distance between a point. Here star is a point and here star is a point. How to calculate the distance between this point and this red line or red hyperplane. Okay, so it is simply mod of, if the hyperplane equation is denoted as g of x, then the distance formula is this perpendicular distance formula is g of x mod by mod w of x. Okay, that is the formula. So now here you can see our SVM is all about finding the optimum decision surface. So red line is also one decision surface, blue line is also a decision surface. But if you select blue line as a decision surface, means it is having very less distance, it is very close to the blue class sample. Similarly, if you select red decision surface, it is very close to red class. So you should find always optimal decision surface. That means optimal decision surface means which is equally separated from these two labels. So you can see this margin, similarly this margin, these two margins. So the margin between, the distance between this margin is calculated with the help of support vectors. So you can see these points are support vectors. Are you understanding? So always you need to find the optimal hyperplane. Optimal hyperplane is the plane which is having high margin. High margin means which is far away from the last point in each class label. So in this red points, this is the last point. That means your hyperplane should be far away from this. Similarly, for blue class, I think this is the last point. So again, from this point also, your margin should be very far away. Okay, your margin should be very far away. So now your objective is, you should find a hyperplane, that means green line, in such a way that you have a large margin. This margin should be more. Similarly, the margin between this red plane and green plane is, margin is 1 by w. Similarly, the distance between green plane or green surface and blue surface is, you can see my cursor, again 1 by w. So the total margin should be maximized. So what is the total margin? 1 by w plus 1 by mod w. So total 2 by mod w, it should be maximized. Okay. So you can see this. So therefore, so what is your important thing is, with the help of support vectors only, we will find the optimal decision surface, that is green. So now what you have to do means, you have to find the decision surface green in such a way that this margin should be maximized. This margin should be maximized. Therefore, what is the constraint here? You can see what is the constraint. So the equation of this line is, this green line is W transpose into Z plus B naught. If you multiply with yi value, it should be greater than or equal to 1. It should be greater than or equal to 1. That is the essence. You can see this. So this is the constraint you have to satisfy. This is the constraint you have to satisfy, where Z is the feature vector and yi is the output. Okay. Okay, this is the constraint. Now the thing is, here the problem is we are actually deriving about support vector meshes. So we have written the constraint. This is the constraint. So if you multiply the output of that point and its decision surface, it should be always greater than or equal to 1. This is applicable for all points. So this constraint should be satisfied for all I is equal to 1, 2, 3 up to n. That means for all the points this condition should be satisfied. Now you need to find the weight vector in such a way that you should maximize this margin. This is the margin equation, 2 by W naught. I already told you now. This is 1 by W and this is 1 by W. Total 1 by W plus 1 by W. So total 2 by W. So instead of calculating the maximization of this, what we are doing is we are minimizing the reverse of this equation. So what is the reverse of this equation? 2 by W naught means the reverse is W naught by 2. So just opposite. So instead of maximizing this equation, you can minimize the half of mod W, okay, or Euclidean norm of W. W is a vector, you need to understand. So now you can write the problem as something like this. So given you are having n samples and each sample is represented by x and its output yi, and you need to find the values of W and B in such a way that you should satisfy this constraint. That means what is the constraint? If you multiply the output and its decision surface, it should be always greater than or equal to 1 for all I is equal to 1 to n. Provided you should satisfy, you should minimize this cost equation. I already told you, maximize this margin is equivalent as minimizing the Euclidean norm of weight vector. Okay, minimizing. So 1 by 2 into Euclidean norm of weight vector you can represent in matrix notation as W transpose into W. Okay, W transpose into W. So now what we will do is, if we are having this type of equations, we want to find the weight vector. Always you can see this equation. For finding the optimal hyperplane, you need to find these parameters W1, W2, W3, W3, W2, W1, W0. These are the parameters you have to find out. So for finding this type of for solving this type of problems, if you are having a number of points and then what is this? This is a constraint and this type of cost function, you have to use a Lagrangian procedure. That means you have to construct the Lagrangian function. So Lagrangian function is given as J of W B alpha is equal to, so what you have to do means, you have to construct the Lagrangian function in terms of cost function, 1 by 2 W transpose W. So you write it, and after that whatever the constraints are there, you add as a negative, as a product of constraints. So here whatever you are having the constraints for all I is equal to 1 to n, you have to add this term in the Lagrangian function, but with minus symbol. So now sigma of this constraint you have to add here, and it should be multiplied with your alpha I, Lagrangian coefficient. What is alpha I means? Lagrangian coefficient. This Lagrangian coefficient is defined for all the input points. Okay, so this is the equation. This is how we will construct a Lagrangian function. This is your cost function, you can see the previous slide, and this is your constraint. So your Lagrangian function is constructed with the help of cost function and the constraints. Okay, with the help of Lagrangian multiplier alpha I. Now once we framed the function, our next job is to find the optimal solution of W. So you take this function and perform the partial derivative with respect to W to get minimum value. Okay, you have to find the value of W such that this whole function is minimized. So you perform the differentiation of partial differentiation of J with respect to dou W. Similarly, there is another parameter B is also there. So dou J by dou B is equal to 0. Then you will get two answers. One is W is equal to, this is the formula for calculating the optimal weights of the decision surface. So optimal weights of the decision weights is calculated as sigma over I ranging from 1 to n alpha I yi zi, where zi is the input vector and yi is the output label +1 or -1, and alpha I is the Lagrangian coefficient. And if you perform another differentiation and you equal to 0, you will get this equation. And what it says means the sum of product of the Lagrangian coefficient and its output, it should be always equal to 0. So that is the logic here. So okay, so you, in this way, after applying the partial differentiation and equal to 0, you will get the formula for optimal weights in the decision surface. So for finding the alpha I, again you can construct the Lagrangian function like this. We can term it as a Q alpha and then sigma over alpha I. You can see this, your alpha should be constant. That means the sum of alpha values, it is always constant. That's why we put this condition. This is your objective function, and then constraint. This constant is added here. Okay, this constant is added. So after solving this equation, you will get optimal Lagrangian multipliers. That means alpha Oi Yi Zi. So optimal weights is given as sum over I is equal to 1 to ns alpha Oi Yi Zi. Okay, alpha Oi Vi Zi. So instead of alpha I, we got here alpha optimum, or you can use also our traditional optimization techniques for finding alpha I. Here alpha I is a hyperparameter. Okay, so here two Lagrangian functions are used. Okay, one for finding the W and another one is for finding the alpha I. After solving this equation, you will get like this. Okay, so you will get optimum WO means optimum weight vector, alpha I means OI means optimum Lagrangian coefficients. So optimum Lagrangian coefficient means your Lagrangian coefficients, it will be non-zero values for support vectors. Okay, for support vectors it will be non-zero values. For non-support vectors it will be equivalent to 0 values. So that is a specialty. So now the next question is, as if you see in our previous diagram, we have seen only the linear patterns, linear separable patterns. If the patterns input points are separable, you can construct a simple decision boundary. Okay, that too it is a simple two-dimensional. So we got simple linear 2D line. Okay, 2D line, simple separable patterns. But in some cases, in most of the cases, the input points are not separable, they are non-separable. Okay, or they are non-linearly non-separable. Okay, in such a case, what we have to do? So what we will do means, instead of applying this whole process directly, we will take a kernel. Okay, kernel is a mathematical function, okay. It can be Gaussian or polynomial or whatever it is. So you take one kernel and you give this set of nonlinear inputs to that kernel, and in the higher dimension it will be separated. The points are all separated linearly. So then that means in higher dimension it will be separable. Once it is separable in higher dimension, you can apply this whole process, like calculating the you frame the Lagrangian equation and then applying the partial differentiation and calculating the weight vector with the help of optimal Lagrangian coefficients. So once you got it, this is how you will solve for nonlinear separable patterns. So you can see this is the same terminal we used. So the only difference is instead of applying directly, we will first apply the kernel function and then we will apply the steps for finding the optimal decision surface. So different types of kernel functions are polynomial kernel function and sigmoid kernel function. The formula, just you have to pass the input and you will get the output, okay. And similarly Gaussian kernel, exponential of minus x minus xi whole square by sigma square, like this. Polynomial, this is polynomial kernel. You can use any one of the kernels and find out the optimal decision surface in higher dimensional. So from this equation, you can see this equation 16, you can frame one architecture also. So if x1, x2, x3, they are all inputs are there, and what we will do means you will apply the kernel, you will apply the kernel function, okay. You apply the kernel function and then you will, after getting the kernel, you can see this, you multiply with the alpha optimum and yi. So alpha optimum into yi, okay. So that is a specialty here, okay. Alpha oi into yi. So you get multiplied with this and then you perform a linear summation of all the outputs. That means here for all the points you have to perform this thing, okay. You have to perform the summation. So finally you will get the output d of x. So just we have written this entire equation in architecture form. This is the architecture of support vector machine, okay. You can note it down. So it also looks like a your single layer neuron, okay. You can see this architecture diagram, okay. So if we are having multiple classes, so far we have seen only binary classes, so that means only two classes, plus 1 or minus 1. What happens if we are having more than one class? So what we will do means we will take multiple SVMs, multi-class pattern recognition for m classes. You can combine multiple CMs given a pattern, and you can give to each SVM is capable of performing binary, okay. So each SVM is performs the binary, and you can combine the output and you can take a corresponding decision strategy like majority voting scheme like that, and you can find the class. This is one type of technique for performing the multi-class recognition using SVM. This is one such architecture. You can also follow different types of architecture. So we are discussing one type of architecture, okay. So finally, in summary, support vector machines involve following steps: nonlinear transformation of data to higher dimension with the help of kernels, and construction of optimal linear solutions in kernel feature space or higher dimensional space. So the complexity of the model is not dependent on dimension of the representation of data. And here the specialty is in SVM, it can be trained with small size data sets, and SVMs can also be used for non-vector type of representation of data also. So if you see in our equations, the performance mainly depends on the kernel. Okay, mainly depends upon the choice of kernel. You can have different types of kernel. You have to try with the different types and see the output and evaluate with the different parameters. So you can also design new type of kernels. You can also define new type of kernels to improve the accuracy also. Okay, so it is a research problem. Okay, this concludes about support vector machine. I have given a brief introduction. You can try to implement using R and Python also, or Python. So you can apply this support vector machines, and you can give any input pattern like data sets, input image data sets, or CSV data sets, or any wine data sets, something like that, and you can train the algorithm. So training means what is happening is it is constructing the optimal decision surface. Okay, thank you, students.